1 over 5n. Well, that works very similarly to 1 over n. We can actually use the limit comparison test. We can see that that we'll get an answer of 1/5 for our limit. And we're comparing a divergent series with our unknown, so this 1 over 5n diverges. Since 1 over 5n diverges, this series right here is known as conditionally convergent. How about the next one, 1 over 5n squared? We can obviously compare that with 1 over n squared. Again, we can do a limit comparison test. We know that 1 over n squared converges. It's a p-series where p is bigger than 1, which means that this series converges. And over here it diverged, so it's conditionally convergent. Over here the series still converges, so this is absolutely convergent. One-fifth to the n here. Okay, so if we think about this, if we were to do the terms, it's 1/5, and then the next one is 1/5 squared, and then 1/5 cubed. This 1 over 5 to the n, that is a geometric series. We keep multiplying by 1/5. R is equal to 1/5, which we know is less than 1. So this converges by the geometric series rule. So let's take this one up here. And our answer is absolutely convergent. And then last but not least, if we look at this n over 5n minus 3. Remember the very first test that we did? Alright, in the term test, we take the limit of the series. If we don't get 0, in this case we don't, then we know that this series automatically diverges. Right? It didn't help us with converging, but it can get us a quick divergence. So this is like the first one. It's conditionally convergent. So we're figuring out if the overall term, ignoring the alternating part, if the overall term diverges, the answer will be conditionally converging. If the overall term, ignoring the alternating part, converges like these two, then it's absolutely